Welcome back to Introduction to Computational Chemistry at Valparaiso University. In this session, I'd like to talk briefly about interpreting results from calculations that are generated by the Gaussian 09 program. And in particular, I'd like to look at structural information such as bond lengths and bond angles. We'd like to know what's the precision of the results that we get from a Gaussian calculation, and how does that differ from accuracy? Precision and accuracy mean two different things. So, what we're going to do is open up the Gauss view windows for the view and the builder windows here, and I think I'd like to illustrate the concept of precision in the structural information associated with a molecule by doing a simple calculation to find the minimum energy structure, which is the equilibrium structure, for methanol. So we'll generate methanol by simply creating a methane molecule in the view window and then replacing one of the hydrogens with an OH group. And so we will think of this as our first trial calculation, and we'll just quickly set this up to be an optimization problem. The method, we'll use the default method, which is the Hartree-Fock method of quantum mechanics with the 321G basis set. For title, I'll give it a title here, CH3OH trial 1, and then we'll submit this. We have to save it, of course, and we'll give it the name CH3OH trial 1. Now, this shouldn't take very long at all to run, because methanol is not a very complicated problem. And while it's running, let me just comment briefly on what the Gaussian program is actually doing. It's searching for the arrangement of atoms in this molecule that makes the most stable arrangement. In other words, that has the lowest energy, because the lowest energy is associated with the forces on all the atoms being equal to 0. And that's what we mean by an equilibrium structure. The forces are all 0. So the Gaussian program, in a very sophisticated way, moves around the different atoms, calculates the forces on them, and then when the forces, it moves them in the direction in which they feel forces, very small amounts of distances, and then repeats the calculation over and over again until it finds the atomic coordinates where those forces are approximately 0. And that's what the equilibrium structure corresponds to. So let's look at the result here, and we'll see that it took 4 steps in order to find this structure here, which is our trial 1. Whoops. Actually, this shows just the initial structure, so if we click ahead to the final structure here, we see it didn't change very much from what the initial structure was, but we can, for example, look at the oxygen-carbon bond distance here, and we'll see that for this level of theory, the value 1.44097 angstroms was found. The question of precision is, how precise is this value? If we were to put error bars on it associated with the calculation itself, how large would those error bars be? And what precision really means in science is, if you repeat an experiment over and over again, how close would the results be to one another? And that's a measure of the precision of that kind of an experiment. So what we can do is a numerical experiment. And in order to do that, we'll keep this trial 1 log window open, but I'm going to go back for a moment to the original starting geometry. Now, it's kind of trivial. If I were to simply repeat this calculation from the same starting geometry, I would get the same answer. But we often don't know a very good idea of what the starting geometry should be. So let me just go ahead and change some of the parameters here. I'm going to go to the Modify Bond tool, and I'm going to change the CO distance from what it originally was. And instead of 1.43, let's make it just a little bit larger. Let's make this something like maybe 1.53, even 1.63. Okay, so let's also go ahead and change the oxygen-hydrogen distance. Okay, and what I want to do is only move atom 2. I don't want to move atom 1. So we'll set atom 1, which is my oxygen atom, fixed, and then we'll just increase the oxygen-hydrogen distance by a couple tenths of an angstrom. Okay, and then to make an even more sensitive test, to vary a few more things, let's change this to the bond angle tool, and let's change the HOC angle. It was originally set to the tetrahedral angle of 109.5, and let's just make that a little bit bigger. Okay, so now we're going to repeat the calculation from a completely different guess at the starting geometry. The method's going to be the same, so when we go up to do the calculation, the only thing I really need to change is the title. So I can verify by looking at the job type, yep, it's still an optimization, and the method is the same. So let's submit this, and the question then is, I'll just change the name of this to trial 2 from trial 1. The question is, how far away will the final answer be from what we got the first time that we did the calculation with the original starting geometry? So it's running now, and in just a second we will get to see. I'm going to minimize the window with the initial structure. We're going to have another result to look at from our second trial, and these are numerical experiments done using the same program but from different initial conditions, from a different guess at the starting geometry. Alright, so you'll see that my initial guess for this one had larger OH distance and larger CO distance, and they don't even look like they're bonded. But now if we look at the 7 steps that it took to reach the final structure, we see something that looks very similar, but the question is, how similar? If we wanted to know the CO bond distance, let's go ahead and look at that. Alright, so we see in the lower left-hand corner, we will see that that distance, oh, I've got to go back to Gauss view, and I've got to change this to inquire. Alright, so the question mark has to be clicked. Now we can look at the CO distance and read it off as 1.44097. Okay, so let's take a look at that value in trial 2. We go over here, click on those 2 atoms, and we get a result that's 1.44095. So only slightly different, just a little bit different, but they are different. Okay, and let's look at a few other bond lengths. Let's look at the OH distance. So over here in trial number 2, it's 0.96577. In this one, trial 1, it's 0.96578. Okay, wow, so those are really pretty close. What this means is that there's a fairly high degree of precision in these values. Let's try something that takes a little bit more sophistication to calculate, and that's the bond angle, which is this COH bond angle. And we'll compare these 2 values in our 2 trials. Alright, so one of them is 110.328, the other is 110.265. That's kind of interesting because it shows that those values differ in the 1/10 of a degree place. And so one of the take-home lessons here is that even though these 2 structures came from running the same program, and the program stopped and said, here's our equilibrium structure, there is some uncertainty, some lack of precision in those bond angles. And it's not, this is actually fairly typical for calculations that I've done, where the first 1/10, the first decimal place, is often uncertain. So here, if we just looked at these 2 values, we would have to say that the result is somewhere between 110.265 and 110.328. And if we did a 3rd trial, we'd probably get a slightly different answer again. And so all I'm trying to get across is the idea that you should be very careful when interpreting bond lengths and bond angles, and realize that there is some lack of precision, some uncertainty in the values that is strictly a numerical uncertainty because of the way that the program runs the calculation. Now the bond lengths that we looked at were actually fairly close in the two cases. Let's take a look at one of the other bond lengths, the CH distance over here. Just for comparison purposes, we'll check on that again, and we'll see that 1.07864, 1.07857. Okay, so there's a difference out in the tenths, hundredths, thousandths, the 10,000ths decimal place in terms of angstroms. And so it looks like, at least for a molecule of this size, that the results are fairly precise for bond lengths, that you can take those digits seriously out to not just the hundredths of angstroms, but probably even the thousandths of angstroms position before you start to see some variation in the results of two different calculations. But we did learn that where bond angles are concerned, that the tenth of a degree place is often going to vary from one calculation to another. So that's what we mean by precision, and realize that Gaussian calculations have some limited precision due to factors that are numerical in nature. Now, I have to distinguish between precision and accuracy, because in terms of accuracy, what we mean there is how close is the result, in this case the result of our calculation, to the result that we would get if we did a careful experiment. Realize that the calculations that Gaussian does are based on approximations, and so though we may solve the equations very accurately, the equations themselves are based on approximations to physical reality. And so that CO distance that we calculate for methanol using this particular level of theory is not going to agree exactly with what we find in nature when we do a careful experiment. And so accuracy has to be judged by comparing the results of one of these calculations to experimental values that have been obtained very carefully. Experimental values themselves will have some uncertainty in them, but the results of these calculations will never agree perfectly because of the approximations that they rely on. And so that amount of accuracy that a calculation has will depend on the level of theory, whether we do a semi-empirical method like AM1, or whether we use a quantum mechanical method like Hartree-Fock, or even something more sophisticated like density functional theory. And it will also depend on the size of the basis set. So I won't get into that here now, but I just do this in order that you realize that these results that you obtain, even though they may go out several decimal places, they have to be taken somewhat cautiously, because even two different numerical calculations can get slightly different values for bond lengths and bond angles. I hope this is helpful as you learn how to use Gaussian and learn how to interpret the results of your calculations.